Hi, my name is Anna Gringaus. I'll introduce myself a little. I work for Visual Studio C++ static analysis team at Microsoft. And I also do a little bit on open source community. I'm one of the maintainers on the GSL, which is guideline support library. It's a small library that supports CPP core guidelines with types. I'm going to talk about static analysis, concurrency in C++, and Visual Studio. Let's start with a few, and I'm going to give some sort of a journey from past to present to future. So let's start with some examples. Let's say we have this quite simple code sample. It's a processor of requests that does quite simple thing. It puts a request in a cache. We can see here that apparently the cache is protected by a critical section. So there's nothing wrong with this code. It's quite simple, easy to understand. Unfortunately, code is never stable. It evolves with time. So eventually somebody comes and adds, wrong way. Add this functionality to the same class, which simply dumps statistic about requests. So now we have a problem. We have one place where cache access is locked, one place where it's not, which is a data race in this case. And it looks like a small problem in this example, but it actually is a simplified version of a real code example, which took a large data center down in one big, very well-known company. So that thing happens apparently in the wild. Another problem with this code is bug happens. It's a problem with any kind of code. Bugs happen and people fix them. And sometimes they're not aware of some things that they're supposed to do or not. So somebody comes later and adds this couple of lines, which is basically bug fix for the case when ID is the same for a couple of requests, and you can choose to handle it differently depending on your scenario. You could return early, you could return an error code, or you could throw an exception. In all of those cases, we will have a problem because on one of the paths out of this function, we release the lock, and another, we don't. So let's see if static analysis can help in this case. So I'll do a short demo of, where's my mouse? Sorry, there's some technical problem here. Yeah, thank you. Thank you very much. Sorry about the technical difficulty. So I'm going to show the same example of the code and how can static analysis help detect this issue. So this is, let's go to the past. This is the same code as I showed on the slide. And let's see what happens if we run static analysis on file on this code. Right click, analyze, and run code analysis on file. So here I'm expecting it to find some problems, maybe not all of that. So right now we see that there's one error that's detected that says that we are inconsistently releasing a log. At some point we do, at some point we doesn't, in the same function. And as you can see, it doesn't detect the second issue where we have a data race. The problem is that semantics of this function is not clear to the checker. So to make the semantics, and not into the user as well, I don't know, for example, if the cache needs to be locked or not. So to make the semantics clear, we can tell the checker and the user that cache is supposed to be guarded by the critical section. So let's see now how we can run code analysis on file and what issues we can detect. So you can see right now that we detect the previous issue, where the we are failing to release the lock on the error path, and the second error, which says we either missing a annotation that says requires lock held, or annotation which means that this function it's a caller's responsibility to hold the lock, or we are or the missing annotation no competing thread, which means that this function never executes in concurrent situation, or it is a data race, in which case this function should log, use the critical section to log around the cache. Let's come back to the presentation. So what if the modern user would, so I talked about demo of the path checker. So in the past, we handled C++, it was mostly C, and we provided annotations, and those tools detected race conditions, data races, locking violations, sometimes deadlocks if you annotate stuff correctly. We have our checkers recognize Windows Locking API. They know what those API do, basically by annotating those API. And we have quite an extensive set of annotations that you can look at on MS-DOCS. Annotations include guarded by, acquires log, releases log, conditional annotations when you acquire or release on condition, for example, success, and others. Locking order, and so on. So let's look at another code example. This is basically the same code example, slightly modified to use modern RAI types from the standard library. So as you can see here, we can use mutex and use logguard to make sure that this mutex is scoped. So in the handle request example, it doesn't matter if you enter early, if you exit early, if you exit via an exception exit or a normal exit, the log will be always released. The second function, however, still has a problem. If you forget to log, you can fix it by a type. So let's see if we can help, if static analysis can help detect this issue still, and if it does or does not create a false positive in the first case. So now I'll go to the present, and let's see if we can run static analysis on file, and see if this example generates any warnings. So as expected, it only generates one warning. There is no problem in the first case. We always release a log. The second still has a race condition. So this demo shows you that the checkers are able to recognize modern standard types. They can recognize that logguard grabs the mutex and releases on an exit. Basically, it understands that destructor of logguard unlocks the mutex. And the checkers understand scoping logs, mutexes, locking API, and more. We probably don't recognize everything, but we keep adding. So how about the future? So C++ evolves very fast and brings very exciting features to the modern and future versions of it. One of my personal favorites is coroutines. Coroutines gives you a lot of power. They give you power in asynchronous case, they give you power in synchronous case. For example, you could create objects on one side, you could thread them through a pipeline and process them on the end, one at a time, and constantly disposing of the object as you go without having to store them, which frees you of implementing complicated state machines. The complicated state machine still exists, but you don't implement it. So here's one of those examples. I have a producer and a consumer. The producer is very simple, it yields 1. It could yield 2 and 3 after that. And the consumer gets those numbers one by one and processes them in a very, very slow manner. So what happens if in this case you need to access a variable that should be protected by a log? In this case, producer function grabs the log, increments the protected variable, and yields 1 to another function. It yields control to another function, where the log is very slow, where the number 1 is very, very slowly consumed. After the slow function finishes, the control is given back to the producer, where the lock is unlocked. So in this case, we held the lock for a very long time, and maybe forever the slow function never exits. Another example of problems with coroutines is not related to coroutines at all. It's related to any concurrent code. In any concurrent code, no matter what the pattern is, there is always a possibility of a lifetime issue. You create an object in one place, you access it concurrently, and at the point of the access, the object might be already dead. It's a lifetime issue. And it's very common in any concurrent pattern. For example, in those cases, when you create a coroutine, when you create a coroutine, you need to be very careful of where the object lives. In example 1, execute coro, we have an X that lives on stack, and we created a lambda called bed that fires a coroutine when called. If you call this lambda without call-wait keyword, you basically fire off the coroutine and immediately exit the function. So X is on the stack, and it's at the point of execution of the coroutine, somewhere in the future, X will be dead. The same example without the lambda async coroutine, it's more of possibility of an error than an actual error, but it's still good to be addressed. So in async coro, this is a coroutine itself, which is passed A by reference. So the coroutine is created, which eventually gets executed, and it increments A. We don't know where A lives. The caller might have it on stack. So A might be dead by the time the coroutine executes. So let's see if we can catch those errors as well, if static analysis can help here. So I'll go to the future. This is our first example with locking while yielding. I run code analysis on file. And now we see a warning, which warns us about suspending a coroutine while holding the lock global mutex. In the second example, I can run code analysis on file and get two warnings, warning me about lifetime of X might have ended when the coroutine is executed, and the same for A. So let's go back to the presentation. So I've showed a small number of examples for coroutine misbehavior. We have much more situations in which they can go wrong. The checker takes care of them. And also showed you the demo of looking while yielding, which creates issues with performance and resource starvation. So thank you very much. This is brought by you by a crew of people, Sani and Sergey and Gabor, who is our summer intern. And special thanks to Gor Nishanov for guiding us on coroutines. As you can see references to the old locking behavior on MS Docs, and please stay tuned for VC blog about concurrency checker and the concurrency checker itself in one of the future Visual Studio versions. Future means soon. So I wanted to talk about new directions as well, which we don't have checkers yet for, but maybe it will be food for thought for you. So we have examples of very complicated user-free patterns, which we are thinking about ways of detecting. For example, in this case, we have one locking section where you can access, you have a table that is guarded by a lock. You want to access this table, and you need to check if your index is in range of the table, of the table's size. So this looking section is checking if I is in the correct range. And then the next looking section is accessing the buffer. What can happen here? What can happen here is table is locked, I is in range, and then table lock is unlocked. So here the competing thread comes and shrinks the array. So in the second section, lock is locked, and we have used an index that is inappropriate size. So now we have a use after free. Oh, sorry. So now have a use after free. So we don't have, we are working on experimental rule to catch those kind of errors. And those errors come from the real-world examples where adversary can shrink your array via functionality in the browser. So that basically concludes my talk, and I would welcome any questions right now. Thank you. Any questions?
So when you analyze the function, you don't really take the caller context into account, right? You just look into the function itself, saying that, oh, potentially you might be doing something wrong. So for example, if caller was actually using memory on a heap and not on a stack, we would not be able to not show the warning in this case.
Yes. So the question is if we take the caller context into account when we are warning about it. We don't. So this particular check I was showing is when we take A by reference and warn on it, it has a warning as it's a potential risk, potential use after free. The reason is because those patterns are really unsafe to use in any case, even if in this particular one it's okay. There is a chance you're going to use it in a different context, in the different context. Somebody else will come and use it in a different context. It's much safer to use it correctly and pass everything by value in this case. We do take caller context into account if you have annotations, like if you have annotation on the function that has releases log or acquires log. And it's basically a contract between callers and callee, so you can check it in caller context as well.
It's an interesting contrast with what was shown or mentioned as part of Herb Sutter's control flow logic when errors that are actually in the code are being presented. But yeah, still different approach. Another question would be, do you plan to build something that is doing like memory model, correctness, usage kind of patterns? For example, like relaxed model. Can be misused. Is it something you are also looking at?
So some of those will be, some of those are taken care by the lifetime checker, I think. Maybe memory model not related to concurrency?
For example, when atomic is used with like on write and read with relaxed model, so potentially threads can go wrong. That can also be like a misuse. So I feel like with some logic you guys could analyze consumer, like writer and reader of atomic variables and see if the right model is being used.
I mean, if you have all the protection in place, but the logic is still incorrect because you have atomicity violation? Like
yeah. Like just using relaxed memory model, for example.
Yeah, we don't currently, but the last example was going into that direction.
Okay, thanks.
Thanks.
For the mutex example, can you tell me what version that was? Was that like 15.6 or 15.6? It's something shipping right now, right?
It's not yet. It's for the future version.
Oh, yeah, I thought that was the later one. Okay, so all of them were. Okay.
So we already have an old checker. So this new checker is basically an old one with an engine replaced and few upgrades.
Okay.
Yeah.
And this question may have just asked, but that I was assuming, I saw you manually having to apply it where Herb's had the green squiggly. Is his presentation showed it putting squigglies, green squigglies showing this is bad code. Is that feature going to be working that way, or is that what he just asked?
So that feature is being rolled out right now, the squiggles in the background. If you enable concurrency rules, you'll get it as squiggles.
When it releases, okay. And I assume also there's a way, can you have it set to fail the build? So for those of us that have old code bases where when we run static analysis, we get hordes of, hey, this should be const expr, this should be this. I'd like something like the mutex to kill the build right there.
Right now there is an ability of check the box when you set up static analysis rule set. You can check the box if you want to run it on build. Right now it gives warnings. I think MS Build has an option of being given error on warnings, and then it breaks the build.
Yeah, treating warnings as errors.
Yeah, treating warnings as errors, yeah.
So say I have an object where just I have a callback or a listener, and I have to be sure to release my mutex before I invoke this callback or listener. I mean, that's my... Say I have some object and I've got a callback or a listener as part of one of my members, and before I invoke this callback, I have to be sure to release my mutex. That's my constraint. If I call the callback with my mutex still held, I'm going to break everything. I'll have a deadlock. Is there a way of enforcing? Is there a way of attributing that to that constraint?
So, tell me if I understand the question correctly. You have a listener pattern,
Sure.
and you have a mutex that controls them on both ends, consumer and producer. Listener and
yeah. Say I'm an HTTP thing, and before I say, hey, I've gotten a request, I have to be sure to release the mutex that I have that's dealing with my networking internals. So before I call that listener saying, hey, I guess something happened, I have to release my mutex because he's going to call right back to me saying something and I'm going to deadlock.
Yes. Yeah, I understand. Yeah.
Is there a way
there's a way to say that. It's an annotation called requires lock not held.
I'm sorry?
There's an annotation that requires lock not to be held at this point.
Okay.
Yeah.
Cool.
And it will warn if you do.
Okay. Cool.
Thanks.
Sorry, just came up with another question. So the function you presented in one of the samples, I think it was like a dump cache map. So yeah, it was clearly a wrong approach. But if there was a function written similarly, but it would be used to initialize the cache. And let's say in our application, we know that initialization happens before we start threads. So it would be safe. So now two questions on top of that. Is it possible to annotate the function like, okay, it's safe use? And would those annotations do something at runtime, or it's only static analyzer hints?
So first question, if you can annotate a function to be thread safe because it only executes during initialization, yes, there is an annotation called no competing thread. That's usually used for the initialization scenarios. The second question, if we can enforce it at runtime, currently no.
So basically, if I have annotation, it doesn't produce any checker code that it's actually true. It's just a hint that I know better, basically.
So it's a hint to the static analysis tool. It could be. We could think about producing a binary, like a runtime analysis tool that converts those annotation into something that can execute at real code and check if the lock is held.
Yeah, I can see how it will be more complicated.
Yeah, that would be an interesting project to do. Yes, we don't currently. More questions? Okay, thank you very much.